I'm Howard Cuckle. I'm a reproductive epidemiologist. I work currently in Tel Aviv, but I also work in New York, Columbia Presbyterian Hospital, and in Leeds in England. And I'm going to talk to you today about choosing a specific kind of cell-free DNA test. But to just go back one step, how do we measure the difference between different tests, between different markers? And it's always to do with the overlap in the marker distribution between affected red and unaffected individuals, which use a cutoff, and that determines a detection rate. That's the proportion of affected with abnormal results, and the false positive rate, the proportion of unaffected with positive results. And the third factor is the predictive value, which is the probability of being affected if your test is positive. So just those three things. With standard screening for Down syndrome, we use multiple markers. The multiple markers are turned into a risk, which becomes an incorporated risk score. And here is the distribution of risks for the combined test. And you can see the overlap in the distribution between Down syndrome and unaffected individuals. Now, here's what it is for cell-free DNA. It's almost as though there's no overlap. There is overlap, but it's a very small proportion. And it's almost a diagnostic test, but it's not a diagnostic test. It's still a screening test, and there is some overlap. But obviously, it's a much better test. I want to show you the actual figures on how good a test it is now by calculating things from meta-analysis, from all of the published literature that maximizes the data we can incorporate to get a good estimation. It averages out the biases between different studies, and it represents a common experience. So it's what you would expect in practice. And here are the detection rate and false positive rates on the left for a combined test, and on the right for cell-free DNA. You can see it reaches almost 100%, not 100%, but it's 99.3% detection rate compared to 84% for a combined test. And the false positive rate is massively reduced from 5% to 0.11%. You can hardly see them, but they're there. And the third thing is, as I mentioned before, other measure is the predictive value. The predictive value of a Down syndrome screening test, the combined test, is only 2%. Only 2% of women with positive results actually have Down syndrome. But in this situation with the cell-free DNA testing, it's half. So this is a very high-risk group that's identified using this screening test. So why isn't everybody doing it if it's so good? Well, one of the reasons is price. It's a critical reason for public health decision-making. So what's the real measure of price or cost? It's the marginal cost, or the ICR. The marginal cost is essentially how much does it cost to detect those additional Down syndrome cases that would have been missed by the old method. So that's the total cost using the new method minus the cost using the old method, in this example, the combined test, divided by the extra cost of doing the whole thing. And that's called the marginal cost. Now, I'll show you what this is based on some calculations or estimations. The bottom scale here is the cost of a single cell-free DNA test. The vertical scale is the total marginal cost in millions of dollars. And if you have a test as expensive as over $1,000, $1,200 a test, then switching means it's $5 million per additional Down syndrome case detected. And of course, if the test is cheaper, it's much less. And the critical comparator is the lifetime cost of bringing up a child with Down syndrome. This may seem a callous calculation, but this is the way public health measures things. If we can get the cost in under the lifetime cost of Down syndrome, bringing up a Down syndrome child, then there is a benefit in financial terms to the healthcare system. And the crossing over point, it gives you the cost that you would need to break even, and it's $450. Based on many assumptions in many different countries, but it's of that order of magnitude. But there's a problem, and the problem is when you switch from combined test to cell-free DNA test, are you going to drop the NT? Are you going to stop doing NT as well as stop doing the biochemistry? And probably the answer is no. And if you retain the NT scan for other things, for cardiac abnormalities, for many other genetic abnormalities you can pick up with an NT scan in addition to aneuploidy, then it's going to be more expensive in terms of marginal costs. And you have to choose a test then, which is a lot cheaper. And the crossover point then is $300. So it needs to be at least $300 or less per test before you can really make a proper public health argument to replace the current testing. Now, some people say, well, cell-free DNA testing, it picks up other things. It's not just Down syndrome. What about those? Well, let's look at that. So here we have, again, the detection rate and false positive rate on the left for Down syndrome, and the other columns are for other things, Edwards, Patau's, Turner's, and other sex chromosome abnormalities. And you can see detection rates similar to Downs, not quite as high as Downs, but similar. But there is a false positive rate at each of those additional, for each of that additional detection, and it accumulates. Here's the accumulation. If you look at the detection rate now, if you're going to do all of those other aneuploidies as well as Down syndrome, then it goes up to almost 0.8% from 0.1%. This is a massive addition, and that has always to be taken into account when doing the financial calculations. And moreover, of course, Edwards, Patau's, and Turner's are much less frequent than Down syndrome, certainly at birth. They may be more frequent during pregnancy, but the key is how many affected births are you going to prevent? So there's Down syndrome, 1.4 per thousand birth prevalence. Edwards, Patau's, Turner's much, much lower. But other sex chromosomal abnormalities are higher, actually, all of them added together. On the other hand, they're more benign, and people rarely terminate extra X or an extra Y. And so there is not a strong argument for adding those into the mix. People will want to add Edwards syndrome and Patau's syndrome into the program because we're already picking those up using conventional non-cell-free DNA screening. What about other things? People are now, many of these companies that are offering cell-free DNA testing have engineered the test to also pick up microdeletion syndromes. And here are the purple ones now, the detection rate and false positive rates for the microdeletion syndromes in comparison to Downs. Less than for Downs, but for DeGeorge, approaching that of Downs. But again, there are false positives and they accumulate. All of those together with the Downs would take you up to almost 1%. And if you're going to do Patau's and Edwards and Patau's as well, and maybe Turner's as well, then you're way up and you're approaching 1.5 to 2% false positive rate, which defeats the object of doing this kind of testing, which is mainly to reduce the number of invasive procedures. These single gene disorders are less common than Downs. DeGeorge is approaching Downs. So if you were to choose one, you'd choose DeGeorge, but there are questions about how benign it is, how severe it is. And that is, again, a public health question that needs to be fitted in the discussion. Now, there's another problem, and I'm going to spend some time talking about this problem, which is the failure rate. There is a no-call rate. Not every test is called. A proportion of tests are no called. The result goes back, we couldn't get a result. Now, that often happens with tests, but this is very frequent. And here are some no-call rates from the literature for the main providers of cell-free DNA testing, ranging from 1.6% to 2.2%. This is quite a large proportion of tests which are rejected as no calls. I want to just go into this in much more detail, so we'll have to bear with me because we have to be a little bit technical here as we go into it. So the left-hand side here is the number of chromosome 21s per genome coming from, and on the bottom scale is the fetal fraction. The fetal fraction is the proportion of all cell-free DNA which is coming from the fetus. Actually, it's more the placenta, but if you think of the fetus and the placenta as one unit, then we talk about it as though it's from the fetus. And a normal case, euploid case, would give you 2 chromosomes per genome, because it's not aneuploid. And as you get more and more fetal fraction, higher and higher fetal fraction in Down syndrome, the proportion will rise from 2 to 3 ratio. And so that's the difference, if you like, between aneuploidy, unaffected and affected pregnancies. Think of it this way. Now, that's just the theory. We have to now throw in the measurement error. You don't know what this ratio is, you're measuring it in the assay. And that introduces assay variability. And here it is. I've shown you an estimate of some kind of variability based on the last slide around what the theoretical average should be. And as you can see, as you get towards lower fetal fractions, there is overlap in the distribution, and more overlap, which is false positives and false negatives. Now, we don't know what the fetal fraction is. We have to measure it as well. So not only do we have measurement error of the cell-free DNA, we also have measurement error of the fetal fraction. And this has a profound effect. So this is the same curve, looks like the same curve, but look what's happened to the Downs. The curve is, the distribution is wider because of the error in fetal fraction measurement, and the curve is flatter. That always happens in an XY plot like this. If you take account of errors in the x-axis, it flattens the curve. And here you can see it's quite a lot of overlap in the lower regions of fetal fraction. And so people have determined that the best cutoff to use to determine a no call is a 4% fetal fraction. Now, not all no calls are due to low fetal fraction. There are other reasons why you may want to no call the results, not enough DNA, many things, but a large proportion of the no calls are these no calls because of low fetal fraction below an arbitrary cutoff, not so arbitrary, but a fixed cutoff of 4%. And that's a problem. Why is it a problem? Because the literature that included in the meta-analysis, nearly all the literature has excluded all of those low fetal fraction samples and is only telling us about the detection rate and the false positive rate in those that are actually called. That means the literature is biased. So you have 2 options then. One option is to have a fair estimate of what the detection rate is to say, I'm going to call, let's suppose you decide to do nothing more when it's a no call. No call is a no call, no more testing, no more anything. Sorry, that's the result. But you'd have to really classify those no calls, the Down syndrome cases among those no calls, as missed cases. So they're false negative in a big sense. So instead of a 99% detection rate, we now have a 97% detection rate. You've lost 2% of detection, equivalent to the 2% of results that end up being no calls. On the other side, you may decide to do an invasive diagnostic procedure on those no calls because we don't know. We don't know. We've lost information. We don't know. I advise you to have an invasive test. If you did that, the detection rate would remain at 99%, but the false positive rate would go up massively because those extra 2% of pregnancies would have an invasive diagnostic procedure. And that's more or less where things are at the moment. There are some other things you can do. You can do some repeat testing, but repeat testing very often of a no call very often also comes back as a no call, because in the time between you did the first test and you did a repeat test, nothing much has changed in the placenta. And that's where the fetal fraction is coming from. Another thing you can do, and it's an option, and it is quite a widely used option, is in those who have failed, is to do an anomaly scan, is to look for anomalies, and if there are anomalies, then do an invasive test. The anomalies, ultrasound anomaly scanning can look at abdominal wall abnormalities, cardiac abnormalities, limbs, bladder, facial, neural tube, and hernia. These are things which are associated with aneuploidy. So if you look at those and see what happens to in practice. In practice, the left-hand side is what happens to Downs. You'll only pick up 64% of Downs using such an anomaly scan, and that's based on second trimester anomaly scanning, not even first trimester. First trimester, probably a lot less. You can pick up quite a lot of Edwards syndrome and Patau syndrome using a first trimester anomaly scan, let alone a second trimester one. So that's not an unreasonable thing to do, to claw back. And you have a particular reason for doing that with Edwards, because in Edwards syndrome, in Patau syndrome rather, the placenta is small, and the small placenta is really the cause of the low fetal fraction, and therefore there are a lot more of those in the no-calls than there are in the calls. Okay, one last thing before I go to a next stage is to talk about twins briefly. Twins are always an extra problem, and the problem here is that if it's a concordant twin, then the number of fetal chromosome 21s per genome is going to be the same as a singleton. But if it's a discordant twin, so one has got Down syndrome and the co-twin is normal, then it's not. It's going to be a lot lower. So you can see, without me drawing any bars, areas around these bars, these lines, that there's going to be more failures in twins. And in fact, this is a real study. This is a study done in London, where they can compare the no-call rates in singletons and twins. It was 2.9% in singletons, and it was 3 times as high in twins. So it's another problem with no-calls. Let's go back a minute to the measurement error around fetal fraction. We can measure it. It's been determined. How do you do that? Well, you get male fetuses, and you look at Y chromosome sequences in the maternal blood. So you've got the truth, you know it's a male fetus, and in these pregnancies you can compare. So you've got that actually allows you, by measuring the Y sequences, to know actually what the true fetal fraction is, and then you measure it using a measurement system, and there is the distribution of errors around a 10%, a woman with a 10% fetal fraction, where it really is 10%. It can be plus or minus 3%, you know, it can go way down, it could be 6%, or it could be 14%. That's a measurement of how inaccurate fetal fraction measurement is. What does that mean in real practice? And we've modeled this, but this is what we estimate, that if you take results that are measured fetal fraction under 4%, then only a small proportion of those red parts of the circle, are really under 4%. The rest, in truth, have got a higher fetal fraction. So there was no need to call them low fetal fraction. Well, can we just get rid of this fetal fraction? The answer is, if you've got, I'll show you what the answer is. The answer is this. If we start off from true fetal fraction for a minute there, and you've seen what the problem is with measurement fetal fraction, the more overlapping distribution, and the number of no calls you have to call. If you had a test a test for measuring cell-free DNA, which is tighter, which is more precise than those in the literature that I've used in the meta-analysis, then you can probably get away with not needing to measure fetal fraction. Just look at the results without distinguishing fetal fraction samples according to fetal fraction. Well, what are the methods available? There are 4 methods available in the literature. The first one is massively parallel sequencing. There are vast numbers of fragments of cell-free DNA are sequenced, counted, and assigned to different chromosomes. That's massively parallel sequencing. Then you have targeted MPS, targeted massively parallel sequencing, where only specific chromosomes are looked at, the ones of interest, 21, 18, 13, and so on. And they are amplified and targeted. So It's cheaper. We're only looking at some sequences, and you don't even need fully sequencing in the end. You can use an array to measure them. So that's the second method. The third method is using SNPs. You can use thousands of SNPs in a multiplex PCR and look at the pattern of the maternal and fetal DNA fragments. And that allows you to calculate by an algorithm the likelihood of being an aneuploidy of some sort, a trisomy of some sort, or euploidy. And finally, there is rolling circle replication. What this does is it takes the targeted sequences, it fixes them into a circle of DNA, and then it uses something called rolling circle replication, which opens out those circles and labels them with a fluorescent label, which then can be measured after filtration using a simple measuring device. So my answer to the question, in a kind of summary here, of what the choice is to choose the latter, to choose a rolling circle. Why? Because there's no sequencing, that's enormously time consuming, requires very expensive specialist equipment. There's no PCR, so you don't have the problems of contamination, of errors from the PCR. It's fully automated, can be simply automated. It doesn't require specialist staff. So it's particularly useful for a biochemical screening laboratory to take out the biochemistry that you've got now and replace it with equipment and very little training to be able to do this. It's affordable because it's simpler, and because it's targeted, it targets Downs, Edwards and Patows, and because it's so simple, it has less measurement error, and you can avoid this fetal fraction measurement, which really gets in the way because of all the clinical implications of these no calls. And the detection rate, as far as we know, and the big studies that have been done so far, is 100% detection for Downs and an even lower false positive rate than I've been showing you for Down screening. And this is with no fetal fraction. So I wholeheartedly support the idea of this method. Thank you.